In this presentation, I'm going to cover a few different approaches for seismic denoising. Seismic denoising is an active field of research, especially in exploration seismology, uh, where array-based techniques are very common. But here I'm going to focus on a specific type of denoising known as time frequency denoising or thresholding, which can be done using single station data or single channel data, better say, which make it more general and applicable to most the type of data that are more common in earthquake seismology. Seismic data almost always contains some unwanted energy, which can be either different type of noise or other type of signals that are not of interest for particular application. One approach to enhance the signal to noise ratio is to prior to the main processes is to use array-based techniques, to which requires having a large array of sensors and sufficient coherency of rivals across the array. If you don't have such an array, your other alternative would be more or less limited to the common spectral filterings. This is what would happen when you bandpass filter and noisy trace. You basically remove some high frequency and low frequency components of the noise, and as a result, improve the signal to noise ratio to some extent. But this would not be this would not do anything about these components of the noise that have the same frequency content as the signal. And as a result, it won't be very effective. In addition, this can sometimes distort your signal and add or generate some artifacts as well. Our approach to enhance the signal to noise ratio is through time frequency thresholding. In seismic acquisition or observed time series is a combination of seismic signal and some additive noise. We can restate the problem of seismic denoising as a non-parametric regression problem. Here, the goal is to estimate basically the underlying regression function, F, or seismic signal, from the noisy observation, but without assuming any particular parametric structure for F. This estimation was mainly Bayesian and linear until 1994, when Donoghue and Johnson proved that a simple thresholding in wavelet domain can yield nearly optimal nonlinear estimation. And the basic idea is to use wavelet transform to basically change the problem of function estimation into a problem of estimating the normal mean of wavelet coefficients. This method, these groups of method basically basically consist of three steps. First, a noisy time series is transformed into time frequency domain. And the second step, wavelet coefficients are modified to basically attenuate those components associated with the noise and find an estimate of signals coefficients. This is done by applying a thresholding function with an appropriate threshold value. The last step is modified coefficients, which provide a sparse representation of our signal, are inverse transformed back into the time domain to reconstruct the denoised signal in a way that minimizes our estimates of risk. So the advantage of this approach over traditional methods is that now the noise, even in the same passband as the signal, can be excluded, and this is done automatically. However, if we apply these traditional denoising approaches that from electrical engineering into a noisy seismic signal, usually they won't be very effective. This has two main reasons. One is the limitation of these simple thresholding functions, and the second is the nature of or usually non-Gaussian seismic noise that violate some of the assumptions used in the noise level estimation. So what you will see in this presentation are a few different approaches to solve these issues and improve the performance for seismic data by either proposing more flexible functions or more realistic noise level estimation through different approaches proposed and published in these papers, which I'm gonna go through them one by one. In the first approach or strategy was to use the major features of data in time frequency domain and threshold each of them separately in a different way. Here I use a macro earthquake data recorded during wastewater injection in Guy Greenbrier, Arkansas, to just demonstrate how this algorithm works. After constructing time frequency representation of the data, in the first step, we use this characteristic function and apply it over the time frequency coefficients to check the existence of basically dominant spectral features that might exist outside of frequency range of macro earthquake. Existence of these features causes the function to have two distinct peaks, so we can use we can check this by distinguishing between unimodality and bimodality of the smoothed version of this function using archaic information criteria. Once we detected them, then we can use or find an optimal scale using Utso's method, and then separate the dominant features into two low and high frequency segments. Next, both segments are synchro-squeeze. Synchro-squeezing is a reassignment techniques that squeezes time frequency coefficients around instantaneous frequencies at each time point to provide more localized and higher spectral resolution. Next, for the low frequency segment, we use the standard thresholding scheme of soft thresholding. But for the higher frequency segment, we first determine the narrow frequency bands of dominant noises inside the frequency range of macro earthquake. This is done in a pre-signal section using the same characteristic functions that we used earlier. And then inside each of these narrow bands of the noise, we threshold the squeezed coefficients using this function that we have specifically defined to take out dominant noise without affecting the main spectral structure of the signal. In the next step, these thresholded coefficients of both segments are put together to form the initial estimates of signals coefficients. We'll then, on the way back to the time domain, we'll stop again in the wavelet domain and attenuate the coefficients one more time, but this time using a customized thresholding function, which has a characteristic between soft and hard thresholding to obtain the final estimation of our coefficients or signals coefficients. In this step, we also detect macro earthquake even using this characteristic function that basically sums the envelopes of wavelet coefficients, which are actually a cross correlation correlation coefficients. So this is equivalent of stacking a few hundreds traces of cross-correlation coefficients resulting from cross-correlating the continuous data with a scaled version of a mother wavelet. So we are doing a type of or kind of template matching here, but without an earthquake template and on single channel data. For the detection and to find the arrivals of these events a bit more precisely, we use an energy ratio function resulted from two basically adjacent moving windows of equal size. So finally, after one more inverse transform, we will have our denoised waveform and detected macro earthquake event. As you can see, the signal to noise ratio have been improved a lot compared to the original ones. Open circles shows the detected event, and as you can see from this zoomed window, the detection function has been triggered very closely to the onset time. So we applied this proposed method to a simple pulse shape signal to check its potential effects on polarity, time shift, and smoothing of the very small emergent arrivals. The first row is the synthetic signal, and the second one we presents its noisy version contaminated by some real seismic noise and some random noise. This is the denoised signal using our proposed method, although the first two cycles of very emergent arrivals have been smoothed out a little bit, and an artifacts has been generated at the end of the signal, but the waveform and spectral structure of the signal has remained unchanged. And the superior performance of this method compared to soft thresholding, hard thresholding, and the bandpass filtering are clearly observable from the following rows. We applied this algorithm to 2.5 hours lengths of vertical seismogram recorded on the surface in Bayou Cornell, Louisiana. Left is the result of automatic denoising and detection proposed here. On the right, we have the result of a well-tuned STLT algorithm running on a bandpass filter data. Our method remove most of the noise and increase signal-to-noise ratio 3 times of the bandpass filtering. It was able to detect a few more events and was more sensitive to small and nearby earthquakes. This is a closer look at the detection events and the comparison of trigger times for proposed and STLK method. You can see that the trigger time for the wavelet-based method are generally closer to the onset time, even for very small and emergent arrivals. So these are quantitative comparison with the other methods. It shows the superior performance of the proposed method. Now, however, as you can see, although the method was much more successful in retrieving the actual signal with much higher signal to noise ratio and similarity of the waveform, it suffered from high computational cost. This motivated us to move and work on a second method where we do all these processing in a single time frequency domain, so it will be faster comparing with to the previous method where there was multiple back and forth in different domains. But to improve the denoising, we performed the thresholding or proposed a 3-step denoising procedure here. So after decomposing the signal into individual modes, in the first step, in a pre-processing step, we use a higher order statistic and calculate the kurtosis of each mode and use it to detect and remove those modes that are mainly Gaussian noise. In the next step, the remaining coefficients, which are a combination of noise and signals, are partitioned into several blocks. The optimal threshold value and the size of each of these blocks, which are very important for the performance of the algorithms, for each level are defined automatically by minimizing Charles Stain's unbiased risk estimator. Then all coefficients inside each of these blocks are attenuated simultaneously using this characteristic function. To use this function, we need an estimates of noise level, which are obtained from a pre-signal window. So here we need a rough estimation of the arrival time in this method. This schema of blocking and thresholding coefficients in groups rather than individually will increase the accuracy of signal estimation by utilizing the information from all the coefficients inside each block. Moreover, this is a data-driven and automatically data-driven techniques and automatically adapt the denoising to the nature of noise and signal in the data. The last step, we will use the thresholded coefficients from these steps as an initial estimation of signals coefficients and use them in a post-processing step to design a wavelet domain Wiener filter and apply it to the noisy coefficients to obtain a secondary basically estimate of the signals coefficients, and the final denoised signal is simply obtained by inverse transforming of these coefficients. So we applied the proposed method to a synthetic seismogram contaminated by some real seismic noise. Here are the results. The first row is the original signal, and the second one is the denoised one using the method that I just described, although there are some attenuation in both P and S coda, but the waveform and the spectral elements of it has been preserved very well. The superior performance of or hybrid techniques compared to the bandpass filtering, hard and soft thresholding are very clear from this plot. The good performance of hybrid techniques can be confirmed by its lower root mean square error and its much higher result signal to noise ratio, cross correlation coefficients. To measure the similarity of the time frequency structure of the signal before and after denoising, we constructed a cross wavelet transform from the wavelet coefficients of the original and denoised signal. This plot shows that the denoising method preserved the spectral structure of P and S energy without affecting their phase information. This is the hudogram of P and S wave window of 3-component data before and after denoising. P particle motions is red, S is green, dashed line shows the average. As you can see, the polarization azimuth of P and S waves and the angle between these two remained more or less the same after denoising. Now let's see some application to field data. The first example is a macro earthquake. Signal to noise ratio was increased from 2.2 to 60, more than 60. So this can improve the detection of small events, which is a challenging task in surface monitoring of macro earthquakes. After denoising, although more clear P and S waves were obtained in addition to these small head wave, which were totally buried under the background noise before the denoising. So this can facilitate the picking and improve the location estimation as a result. The second example is an OBS seismogram recorded in Cascadia. Noise is very strong and relatively long period. Our method was successful to remove these high power noise and increase the signal to noise ratio from 1.1 to 346. In summary, we can say this method is both faster and more accurate than the previous one. However, it is still slow for long duration seismogram and for real-time processing. Because of this, we kept or continue working on a third method. In this method, we use short-time Fourier transform instead of wavelet, which is faster to compute. We do all the thresholding in one step, but we use more sophisticated noise level estimation procedure based on the minimum statistic approach of Rayner-Martin. In this approach, it is assumed that the signal is always stronger than the noise. Thus, if we track the minima of noisy power spectrum with a sliding window, we will have an estimate proportional to the background noise power. Based on this, we use a more mature recursive averaging approach proposed by Cohen, where the averaging is done by time varying, frequency dependent smoothing parameters that is adjusted by the probability of a signal's presence. This procedure basically consists of two iterations of smoothing and minimum tracking. In the first iteration, a rough estimation of signal presence is made in each frequency band. Then in the second iteration, the smoothing exclude basically the relatively stronger signal component and past spectral power values of noisy measurements during the periods of signal's absence are recursively averaged. Using this, we will have an estimation of noise level from the whole duration of seismogram and without requiring any arrival time information. Then we segment the time frequency plane into a few disjoint macro block. And next, we threshold the coefficients inside each of these blocks, but this time one by one. However, based on a threshold level and values that is estimated from all surrounding coefficients inside these smaller macro blocks. The thresholding function and the selection of the size of these blocks and thresholding levels are similar to our previous method. Applying the new methods on same synthetic seismogram with different noise level, we see that the algorithm is successful in removing the background noise and improving the signal to noise ratio. However, for some of the low signal to noise ratio, this algorithm remove some part of the signal, but this might not be problematic for some applications such as detection that focuses on focus of denoising is more on improving the signal to noise ratio rather than keeping the details of the seismogram. If we compare this method to other techniques, although it does not achieve the performance of hybrid methods that we proposed earlier in terms of root mean square error, cross correlation, however, it is, as you can see, it's much faster than the previous one, so it can be used for real-time processing. So this and does not require any pre-information about the arrival time. So this could have different sets of application compared with the previous method. This is a 2-minute seismogram recorded in Guy Greenbrier. As you can see, in addition to the wide spread random noise, these coherent noises within the frequency range of signals also have been removed, and signal to noise ratio was increased significantly. This method is almost 10 times faster than previous one. However, it is less accurate in terms of keeping the details of seismograms like coda part and or emerging arrival, but still useful, as I said, for some application like detection. And finally, in our fourth method, we kept or we went back to that three-step thresholding scheme, but for the thresholding step, we used hard thresholding, simple, much simpler, less complicated function, which is one of the traditional methods. However, this time we totally skipped the noise level estimation process by using a general cross-validation function, which basically mimic that risk between the true and estimated signal, and is just a function of threshold value. So we can use this to mimic and to use the minimum of this function as an optimal threshold value. Another difference is that we do the main thresholding this time in synchro squeezing domain, while in the post-processing step is simply applying a secondary thresholding in the wavelet domain. Another advantage of using a hard thresholding is which is a simple function, as I said, as the main thresholding function, is that now it became easy to implement this method in a reverse manner to remove the signal's energy and keep the noise. I have explained the synchro squeezing before, but from this figure you can see how it increases the localization compared with the short-time Fourier transform and wavelet transform. So now we will use this characteristic and perform the thresholding just along the ridges or these curves, which are the main elements of our signal. So now instead of processing of hundreds of traces of wavelet coefficients, we just need to threshold or process the coefficients along only several of these curves in the synchro squeeze domain, which would increase the efficiency and speed of our denoising process. So first, applying the algorithm to the synthetic seismogram. In this figure, I have plotted the denoise signal on top of the original one. As you can see, in overall, they match very well, except at the very beginning of the P arrival and the coda part. The second figure shows the result of the reverse algorithm that automatically removed the seismic energy from the noises seismogram without affecting the spectral elements of the background or ambient noise. This would be really useful in ambient noise processing studies. Wavelet power spectra before and after denoising are presented in this figure. To measure the similarities of these two representations, we constructed the cross wavelet and wavelet coherency spectra. The cross wavelet transform highlights basically the region in time frequency spectra where two spectra have high common power and represent their local relative phases with these arrows, while in the wavelet coherency shows the region where the two spectra co-vary but not necessarily have a high power, and is equivalent to localized cross-correlation in time frequency space. As you can see, both of these plots indicate that the spectral structure of P and S wave have remained untouched after the denoising, and their phase information has not been affected. Again, these are the hudogram of P and S wave window from the three component data before and after denoising. What you see is that the polarization azimuths of P and S waves and the angle between these two remain more or less the same after denoising. So denoising does not affect the polarization of the wave. These are the results of our new methods compared with the block thresholding method, soft thresholding, hard thresholding, and bandpass filtering, an original one and the original signal. In this method, it is faster than two algorithm, but not as fast as the third one. However, it is the most accurate one in terms of keeping the details and waveforms and shapes of the signals. The first field examples are three-component obvious data. As you can see, our proposed method automatically remove the noise and increase the signal-to-noise ratio from 2.2, 2.7 to over 165. The second example is from Guy Greenbrier, before and after denoising. And these are the result of reversed algorithm on previous OBS and microseismic example. As you can see, seismic signals, even in this case, that have been completely buried under the background noise before the denoising has been distinguished automatically and removed. This can be helpful for pre-processing of ambient noise. You can see from this example that the method tends to keep the noise in the background of the signals and without affecting the structure of spectral elements of the ambient noise. The second example includes the borehole, near surface and surface recordings of microearthquake associated with an underground collapse of a cavern in Bois Cornell, Louisiana. 7 events are clearly observable on the seismogram recorded at the bottom of the borehole. But as we go toward the surface, the noise level is increasing, covering these microearthquake signal to noise ratio for the near surface data has been improved after the bandpass filtering. However, the bandpass filtering did not help that much for the case of surface data, mainly because of these high frequency noises with the same frequency range as the macroearthquake. On the right panel are the result of our denoising approach, where you can see that it works for all the traces and significantly improve the denoising, which can be super helpful to identify these and detect the macroearthquake buried in the noise. So denoising is one of the main seismological tasks in which deep neural network has been extensively used in recent years. So in as the last part of this presentation, I'm going to briefly touch on these. Deep learning-based approaches for seismic denoising can be grouped into two main categories of supervised and unsupervised technique. In supervised approach, a deep neural network is used to learn a complex statistic of noise and signals directly from a large-scale realizations of the noisy data and suppress it more flexibly using the universal approximation property of neural networks. However, the performance of these groups of methods is, in practice, highly depends on how well these semi-synthetic and training data sets represents the real-world data, which is a challenging task. So to overcome difficulties of obtaining a good distribution of realistic noisy data and their clean pairs, the unsupervised methods rely on the sparse representational learning characteristics of neural networks, some variants of them like autoencoders, to attenuate the uncoherent noise without a need for labels, or to use generative models to learn basically domain mapping from noisy data domain into the clean signal domain. Autoencoders are type of deep neural networks. They first encode an input signal into a low dimension feature set and then learn to decode it uh, back into the original signal. And in this process, they learn to basically ignore the less important features or weaker components of the uh, input signal that usually correspond to the noise. So although these models do not require any clean signal or noise labels for training, they are often only effective for random noise removal. A more effective unsupervised approach uh, that would work also for incoherent noises as well is to use generative adversarial networks, although still some examples of clean and noisy sample data would be required in this approach. They do not need to be paired. So this approach basically learn the domain mapping rather than like pairs, learning the relationship between pairs of signals. So let's bring back one of those slides that I presented earlier. This was the main procedural time frequency denoising approach. We can do actually a very similar thing using neural networks. For those of you who have worked with autoencoder, this L2 norm should be very familiar. Autoencoders are basically learning to copy their input uh, to the data input to their input layers to the output layer in a way that they basically reconstructed the loss by reconstructing this by minimizing this similar L2 norm loss. To increase the sparsity here, we can add actually a constraint to the loss function that pushes most of the neurons in the hidden layer to be close to the zero. So this is essentially equivalent of to thresholding procedure that we were doing in denoising, which promote the sparsity. Based on this, in the design of deep denoiser, a unit, a neural network with a much lower dimension at its bottleneck was used, which acts similar to that sparse autoencoder, with this difference that here the sparsity was imposed explicitly in the architecture of the network. The network simultaneously learned sparse representation and how to map it into two masks that we formulated them as Wiener filters, which can be used to decompose the noisy data into signal and noise. So these are some examples. We added actual recorded seismic noise and seismic signal and noise together to form this noisy trace, which will be input to the neural network, the trained model, which decompose it into recovered signal and noise. We see that there are some leakage of signal, but still the recovered form is very close to the original one. This works on a strong coherent noise, although there are some leakages still. Another example is a very periodic, I was calling signal, not noise anymore. That's another example where these techniques can be used to decompose two overlapping signals from each other. Applying these techniques blindly to a lot of noisy data in North California, we saw that it can be useful in improving the signal to noise ratio of the data, which can be quite useful for detection and earthquake monitoring tasks. This is an example showing how much the denoising can increase the characteristic function of STA-LTA method. which has room to improve which suggests the improvement in subsequent detection. So in summary, we've seen several data-driven techniques for automatic seismic denoising. Each has some advantage, some disadvantage. They might be appropriate for different use cases. If you were interested, I suggest you to check out our papers and the codes that are available for all of these techniques that I've talked about in this GitHub page. With this, thank you for your attention.